my name is Elza Moore. I am a senior undergraduate student at Scripps College, majoring in mathematics, and I will be presenting on how to construct the rational numbers using basic concepts in analysis and relations on sets. So first I'm going to say that we are starting off our construction assuming all of the properties that we know about the natural numbers. So those are the properties that we very easily observe in the real world, hence the natural numbers. So from the natural numbers, we know that we have the properties of addition and multiplication. So we're going to assume that in everything that we're doing. So the first step towards the reals, well, we're doing the rationals, but it's also the first step towards the reals, is to take the natural numbers to the integers, which we can do by defining notion of subtraction as an additive inverse. So we're in the natural numbers, we don't have subtraction yet. So how are we going to get negative numbers? We don't have any concept of an additive inverse in the natural numbers. That's why we don't have the negatives. So in order to start to understand the strategy for defining subtraction, we'll first need to define a relation. A relation on a set X defines the relationship between two subsets of X, A and B. The relation is a set of ordered pairs, A comma B, where A is an A and B is an B. So the set is also the subset of A cross B, and we're going to use this squiggly symbol to define a relation throughout this presentation. So now that we've defined a relation, we can talk about something called an equivalence relation, which is a type of relation. It's a relation on a set that's reflexive, which means that A is always related to itself if A is a member of the set. Symmetric in that if A is related to B, then B is related to that implies that B is related to C and vice versa. Transitive, meaning that if A is related to B, B is related to C, that implies that A is also related to C. So these are things that, we kind of learn in grade school, the idea of something being transitive. But now we're kind of generalizing a lot of these concepts so that we can extend them further and really get to the heart of what we're talking about when we talk about these concepts. So an equivalence relation, what it does to this set X is it partitions the set X into disjoint subsets called equivalence classes. So what it means to partition a set is if you have some into disjoint subsets, you have some set of items, and you can split that set of items into subsets of those items. So little, smaller sets that contain elements from the larger set X, and they're disjoint because none of the sets contain the same. All of the sets contain a unique, there's no overlap, there's no intersection between each of these subsets. And we say that they partition the set X because we know that they encompass all of the elements of X. So every single thing that's in X must be in one of these partitions, must be in one of these equivalence classes. So yeah, we're saying here two elements A and B are in the same equivalence class if you can define an equivalence relation between them. So if A is equivalent to B, where, if A is related to B, where this squiggly is an equivalence relation on X, then you would say that A and B are in the same equivalence class. So we need those notions to construct Z, the integers, from the natural numbers, and because we need to introduce this notion of subtraction, as I said before. And so the way that we're going to do that is use a familiar property of n, which is addition, along with an equivalence relation on n to define subtraction using addition. So we define our equivalence relation on n as follows. I've called it just R negative, I don't think that that's standard notation, but it's what I'm using, as this two sets, two ordered pairs A comma B is real, like, and alpha comma B are related to each other if and only if A plus beta equals B plus alpha. So what you see here is, if you can remember from grade school, if you were to subtract alpha from both sides on the right, and also subtract beta from both sides on the right, you'll get this A minus alpha equals B minus beta, and you can define that as your negative numbers, basically. So in the previous example, the negatives in the integers are defined as the set of equivalence classes. So each negative number is assigned to a certain equivalence class, which is made up of these ordered pairs that all are equivalent to each other by this equivalence relation that we defined. So that is, like, if you want to know what is a negative number, the negative number is the equivalence class of all of these ordered pairs, and all of the negative numbers are all of the equivalence classes of these ordered pairs. So now that we have the integers, now that we have subtraction, and we've defined the negative numbers using our equivalence relation that defines subtraction and the idea of equivalence classes, our next step to constructing the rational numbers, now we have all of Z, because Z is the natural numbers, which in this talk, we're assuming that the natural numbers include 0, but Z is all of the natural numbers and all of the negative numbers. So now we have the negative numbers. So now what we need to do is somehow use what we know about the integers to construct the rational numbers. So just checking in here, we can now use all three of these. We can use addition, we can use multiplication, and we can use subtraction, because we've defined all three of these operations in the integers, but we have not yet defined the key property in the rational numbers, which is division. So that's our next step. It turns out that we can use a similar process to define division, which is the missing piece in our construction of the rational numbers. So we can define an equivalence relation. Instead of before we define an equivalence relation using addition, now we can define an equivalence relation using multiplication. So I'm going to define this, I call it the division equivalence relation, also not standard, but I'm going to define it as this relation between these two ordered pairs. A comma B is related to alpha comma beta if and only if A times B equals beta times alpha. So this is going to give us our notion of division, because it's going to give us these equivalence classes that we can call this A over B, and everything in this equivalence class belongs to that particular rational number. And obviously in our standard notation in mathematics, we usually call that equivalence class, we label it with the most simplified version of that rational number, but all of the other ones are in that equivalence class as well, because they are equivalent based on our previous equivalence relation. So now we have all of the rationals. More can be done to go on further and construct the reals, but I'll only be talking about the rationals in this talk. And to touch on things that you would need to check in order to make sure that we are indeed working with the rational numbers, is you would need to make sure that all of these operations do indeed work. So you can use multiplication, you can use subtraction, you can use division, you can use addition. you have defined this notion of a rational number as these equivalence classes. And you also need to know that these definitions that we've created are something called well-defined, which means that they don't depend on what you call them. And I'm not going to go into them being well-defined right at this moment, but that is important for making sure that we know we've actually constructed the rationals, because if they're not well-defined, then these operations are not similar to the rational numbers that we do know. So yeah, that's all for today. Thank you for listening to my talk. I drew Snoopy guiding us through the wilderness of the real numbers and their construction because I love Snoopy. Anyways, have a wonderful day and thank you for listening.